Welcome. I'll begin by interpreting the problem statement. We have kerosene and it's flowing through a 1/4 inch diameter tube. Goal 1 is the mean velocity in the tube. So if we call this section 2, our first goal is V2, which is the mean velocity anywhere in the tube. And then we're looking for the discharge. So we want to find the discharge. And we're told to assume that the only head loss is in the tube itself. Connect this to my everyday world, and so this is a classic draining tank problem, and we have a very small diameter tube. So I know two things. One, I know that the flow in here is going to be viscous, so viscous effects are going to be very significant, and of course the problem statement said there is head loss. And the other thing I know is that this is a very tiny tube, so I would expect a very slow flow, so I'm going to guess that I've got laminar flow in the tube as opposed to turbulent flow. Let's go ahead and get started with the problem solution. As always, I document my work. Notice that I convert diameter to feet, and these sections in the datum, I added these later actually when I hit that part in my problem solution. I assume steady state, which means that the properties stay constant with time, and that's not quite true, but it works really good for this problem. I documented the problem assumption, all head loss occurs only in the tube, and since I assumed laminar flow, I'm going to use a kinetic energy correction factor at section 2 of 2.0. When I needed fluid properties in my solution, I came back to this section of my documentation, and I wrote down fluid properties here. Goal 1 is mean velocity in the tube. Goal 2 is discharge in the tube. And to find this goal, I started with the energy equation, and I'm going to apply this from section 1, which is on the top of the water surface, to section 2, which is at the exit of the tube. So I wrote the general form of the energy equation, and then I did term-by-term analysis. So this is the pressure on the top of the water surface, and it's 0 gauge. The velocity at the top of the water surface is moving, but it's very nearly 0, so I set that term to 0. The elevation at the top of the water surface is known. There's no pumps or turbines, so I threw those terms out. The head loss isn't presently known, so I made that an unknown. The pressure at the exit of the tube across the plane of the tube, as always, is 0 gauge. My goal is a velocity at section 2, so I marked it with the goal symbol right here. And lastly, Z2 is 0. I should have written down 0 there, because Z2 is the datum. And so the energy equation cooks down to this expression right here, and I can see it has my goal in it. My goal is right there. And I need to find the head loss. So to find the head loss, my idea is apply the Darcy-Weibach equation, which I'll do next. So the Darcy-Weibach equation describes the head loss in a straight run of pipe or tube. Here's the equation. My new goal is the head loss in the tube. There's the goal. And I know the length of the tube and the diameter, so I know that, and I know that. And I've already counted the velocity at section 2 as an unknown, so now I'll count it as a known. I know the gravitational constant, so I have one more unknown, which is the friction factor, F. So that becomes my new goal. For the friction factor, as an engineer, I select a correlation, and for laminar flow, here's the appropriate correlation. The friction factor is 64 over the Reynolds number. So my goal is right here, the friction factor, but I don't know the Reynolds number. And here's the equation for the Reynolds number. The Reynolds number is velocity times diameter divided by kinematic viscosity. And I know all these parameters, V, D, and nu. So the result is I've got this problem cracked. I have 3 equations, the energy equation from 1 to 2, the Darcy-Weibach equation for the friction factor, and a correlation for F, which is the friction factor. And then I have 3 unknowns, the friction factor, the head loss in the tube, and the velocity in the tube, which I've called V2. So once I've found V2, I can multiply by area at section 2 using this equation, and then find the very last goal, which is the discharge in the tube. One of my plan is to solve for V2. And to do this, I'm going to have to solve equations 1, 2, 3, and 4. And my notation here is I've numbered these equations as I've went through this solution with boxed numbers. And there's two ways to solve these equations. Method 1 is program the equations in a computer and have the computer do the work for me. And method 2 is algebra. And for me, I definitely prefer having the computer do it. But in this solution, I'm going to show you how to do it with algebra. And once I've done this, I will then have V2. So my next step will be to calculate discharge with the flow rate equation. And then the last step of my plan is I'll come back and check my laminar flow assumption. In particular, I'll calculate the Reynolds number based on pipe diameter and see if it is indeed less than 2,000. So I started by combining equations 2, 3, and 4. So here's the Darcy-Weibach equation, and then I put in the correlation for the friction factor right there, did some algebra, and I derived a new equation for the head loss in terms of problem parameters. So this becomes equation 5. So next, I put equation 5 into the energy equation, which is equation 1, and I rearranged terms, and it came out like this. So this becomes equation 6. And what you want to notice here is that this is a quadratic equation. V squared plus a constant times V minus another constant equals 0. Then I took this equation and put numbers into it. So here's the B parameter right here. So I calculate that, and it came out to be 18.8 feet per second. Then I calculate the constant C, given right there, and that came out to be 16.1 feet squared per second squared. The result is right here, and what you want to notice about this is that the units of each term work out to give dimensional homogeneity to this equation 7. Next, I solved equation 7 with the quadratic equation formula, and I noted that the constant C was minus, and that made this term right here positive, and I put numbers in there, checked units, and the velocity at the end of the tube came out to be 0.821 feet per second. Now that I know the velocity at 2, I can calculate the discharge with the flow rate equation. Here's the numbers, and the discharge works out to be 2.8 cubic feet per second. But this number is way too high, so I went and checked my calculations, and this number should be 2.8 times 10 to the minus 4 cubic feet per second. Let me go ahead and fix that. All right, now I have the correct value of discharge there, and this is a good example where it's always good to check your numbers against reality. A flow rate of 2.8 CFS is a huge amount of flow, certainly way too big for a 1/4 inch tube. My last step is to check the Reynolds number. Here's the formula I used. I put in numbers, carry and cancel units. The Reynolds number came out to be 671. My criteria for laminar flow is 2,000, and I see that the Reynolds number is less than 2,000. Therefore, my assumption of laminar flow is a valid assumption. In review, when I see viscous flow in a pipe like this, I always think of applying the energy equation with head loss, calculating head loss with the Darcy-Weibach equation. It's very common in pipe flow problems to have to guess that the flow is either laminar or turbulent, and then you check your guess by calculating the Reynolds number, as I did in this example. The last review comment, computer solutions in general for viscous flow problems such as this one are much faster, and that's generally how I solve these kind of problems. And hey, I also love computer programming. That concludes this example. I hope you found this very useful, and thank you again for listening. We'll see you next time.